Morning, everyone. Yeah, it's very windy here today, and the power went out 3 times already. So we're gonna hope for the best. Let me just finish setting everything up here. How's everybody doing? Questions in the meantime? There'll be no music today. We're already running late. All right. So questions? Last time we saw how the derivative of inverse secant is this if you restrict the attention of secant to a certain interval, right? And the interval we took, well, let's look at secant again. Secant, which is 1/2 cosine, so it's going to look like this. And then like this. And so on, right? I mean, periodic of period 2 pi. Well, I mean, we're going to redo it. So first of all, the derivative of inverse secant is this if we restrict the attention of inverse secant to this interval and this one here, right? So we have taken these two intervals. So this is true, well, for secant restricted to the interval 0 to pi over 2, and then pi to 3 pi over 2. And that's what our book does. So for us, this is the derivative we're looking for. But as suggested, other books will do something else. And it makes a lot of sense to use the two adjacent intervals to define the inverse secant. So let's investigate what happens in this case. Suppose we restrict secant x to the interval 0 to pi over 2 and pi over 2 to pi. What happens then? And for those who wanted us to do this again, you'll see we're going to do it from scratch. So you'll see how everything comes up. Right, so if we define, so using this, define the inverse secant, right? And then the question arises, what is dy dx in this case? If everything goes well, the midterm should be done over the next weekend. So by the next, well, so let's say by Monday of next week, you can expect grades to be out. Right, so, take secant of both sides, the usual, and then differentiate with respect to x, assuming y is a function of x, derivative of secant is secant tan. And derivative of x is 1. So dy dx is 1 over secant y tangent y. Right, same thing as before. Same thing as before so far. And now, what we would like to do is rewrite this tangent in terms of secant so that we can replace by x. And now let's look at this for a moment. You know the graph of tangent, right? The graph of tangent looks like this. So tangent is positive here, and tangent is negative in this region, right? So positive in 0 to pi over 2 and negative in pi over 2 to pi, right? So what's going to happen? This, you're going to have to split that up into two pieces now, right? This is going to be 1 over secant y, absolute value of tangent y, when y is in 0 to pi over 2. And then it's going to be negative of that. If y is in pi over 2 to pi. Right? Because absolute value of tangent y in here is going to be negative tangent y. So you need a negative to compensate. Negative gives you positive. Very good. So now we're in the usual situation, right? This now becomes 1 over secant y square root of tangent squared, which is 1 over secant y square root of secant squared minus 1. I don't want to erase any of that. I may need it. So this becomes 1 over x square root of x squared minus 1. And similarly here, this becomes, well, I mean, it's the same thing, right? It's exactly the same thing. So it's negative 1 over x. Let me leave the secant y as secant y for a moment. So this is going to become negative secant y times square root of x squared minus 1. So it's either this, if y is in here, or it's this, if y is in there. But in here, in 0 to pi over 2, secant, which is 1 over cos, secant is positive, right? Because the cosine looks like this. And in here, secant is negative. So here it's going to be secant y if secant y is positive, and here it's negative secant y if secant y is negative. And you know what that means. That means that it's really the absolute value. Right? So this whole thing can be rewritten as absolute value of secant y. And secant y is just x, so it's 1 over absolute value of x times x squared minus 1. There it is. And this is how I learned what the derivative of inverse secant actually was. So depending on what book you pick up, there's no consensus. So you want to be careful. How are we doing here? Do we want to discuss the inverse cosecant just for completeness? Sarah's asking which one is used in our book. The one without absolute values. The one where you define, where you take secant on these two intervals, so there's no need for the absolute value. So we are using the textbook domain, absolutely. For cosecant, I'll let you redo the whole argument. No, well, maybe we should do it. Cosecant is 1 over sine. So the graph of that is going to look like this. Right? It blows up at 0 and pi, because that's when sine is 0. Not 1-to-1 again, but if you restrict your attention to certain intervals, you're good to go. So which intervals are we restricting our attention to for the inverse cosecant? Let's work it out. I don't even know what the answer is, but we'll work it out. Leela is asking, do we have two derivative equations? Do we have to split it up into a piecewise defined function? And the beautiful observation is that you do not, because even if you do, they can be rewritten in one nice expression, namely 1 over absolute value of x squared minus 1. Jack, we're doing inverse trig still. So if we're looking for the derivative of inverse cosecant, in other words, cosecant y is equal to x, so the derivative of this is negative cosecant cotangent dy dx. So dy dx is negative 1 over cosecant cotangent. And what's going to be important is the cotangent here, right? Our hope is that we can rewrite this as absolute value of cotangent y. So we need cotangent to be positive. But cotangent is cosine over sine. So in the interval 0 to pi over 2, so first of all, it blows up at 0 and pi. And in the interval 0 to pi over 2, both cosine and sine are positive, so it's going to look like this. And then in the other way, it looks like that. And same here. So what do we need? We need cotangent to be positive. And cotangent is going to be positive in this region and in this region. Come all the way to here. And there's your answer. There's your answer. In order to define the inverse cosecant, we're going to restrict our attention to the interval 0 to pi over 2, union pi to 3 pi over 2. There it is. First and third quadrants, if you will. So then this becomes negative 1 over x square root of x squared minus 1. There it is. Very nice. Shall we do a few exercises from the book? Now that you have committed the derivatives of the inverse trig functions to memory, Sophia, indeed, this will absolutely have to be the interval the book uses. And once again, if you choose a different interval, then you're going to have a different derivative. Possibly one with absolute values again. So different books will have different answers for the derivative of inverse secant and inverse cosecant. We're still on page 224. We're asked to differentiate the following function. What's the derivative? Well, derivative of inverse secant. We don't have it here anymore, but you know what it is. It's just this. But now chain rule kicks in, right? So what do we have here? We have an inverse secant of something. So the derivative of inverse secant is 1 over x, square root of x squared minus 1, times the derivative of the inside. Simplify some stuff. This becomes 1 over square root of e to the 2x minus 1. Derivative of arctan of x squared. You know the derivative of arctan. Derivative of arctan is 1 over x squared plus 1. So the derivative here, 1 over that square plus 1 times the derivative of the inside. or 2x over x to the 4 plus 1. Is everybody with us here? Questions? Still very windy, so if the power goes out, wait for me, I'll be back. Same question, we're looking for the derivative. There is no difference, right? There is no difference between arc cos and inverse cos. They both refer to the same thing. I mean, the problem with this notation is that people who aren't accustomed to it might believe for a moment that you mean 1 over secant, which it is not, right? Is everybody absolutely comfortable with the fact that this does not refer to 1 over secant, right? It's notation for the inverse function. As people are suggesting here, derivative of arc cos is -1 over square root of 1 minus x squared. So 1 minus this squared times the derivative of the inside, which is 1 over 2 root x. You have to derive the root x, absolutely, right? Chain rule. Chain rule kicks in. So this is -1 over 2 root x, square root of 1 minus x. Right, I mean, it's very important that nobody confuses this notation with 1 over secant. So that's why the other notation is good, the arc secant, right? In that case, there's absolutely no confusion possible. I mean, you could rewrite this as 1 over 2 root x minus x squared if you wanted to. A bit better. You do not need to prove the derivatives of the inverse trig functions on the exam unless the question is specifically asking you to do that. Which, well, it probably is one of the odd numbered questions in the book, so it's fair game. Would you need to put absolute values of x? I guess I was a bit sloppy here. You probably should. You probably should. But here, in this domain, it was understood that x had to be bigger than or equal to 0. So I guess you don't really need to, because right? I mean, you can't move away from the domain when you're taking the derivative. So you're good to go. Yes, sorry, minus, thank you. Thank you for that. Why would you need to put absolute values? Well, it's the square root squared, right? So this should always be positive. Whereas now, if you just write in terms of x, it could be both positive and negative. but because of the domain, but also because of this, right? Here, you cannot have a negative number. So many reasons why you're still fine. In question 66, do we combine the exponents of the denominator after we derive it, or will it stay the same? Well, I think it becomes x to the 4, right? So if there's a square root in the denominator, I must always put absolute values. Well, I mean, be careful here. It depends on the question, right? Look, I mean, the point is the square root of x squared, you know, to be the absolute value of x. And that's essentially what you have here. That's all we're saying. So we were saying we should be careful, and this should really be absolute value of x. But then going back and looking at the domain, we understood that x had to be 0, bigger than 0 anyways. That is x to the 4, yes. X to the 4. Oh, in question 70, x to the 4 as well. X to the 4 as well, yes. Sorry, I was running out of room. Ln of arc10 x to the 4. So what's the derivative? Derivative of ln is 1 over. So 1 over arc10 times the derivative of the inside. What's inside? Inside is arc10, whose derivative is 1 over x squared plus 1 times the derivative of the inside. Inside is x to the 4, whose derivative is 4x cubed. Thank you, Eddie. There it is. Let's do one more. Take the derivative and simplify completely. I think this simplifies nicely. Fine, if you want. I mean, it doesn't really. It's always asking if we should simplify 70 into one expression. You should, but I mean, it's essentially the same thing. But speaking of simplification, I believe, you know, I didn't try this one yet, but I suspect that it's going to simplify greatly. So let's do it. Derivative of arc10 is 1 over that squared plus 1 times the derivative of the inside. Times 1, derivative of x is 1. Here you've got a square root, so derivative is 1 over 2 square root times the derivative of the inside times 2x. The 2's cancel out nicely. Maybe we want to expand the denominator here. This is x squared minus 2x square root plus 1 plus x squared plus 1. And this is 1 minus x over the square root. So keep going. Maybe I was reading too much into that. Maybe it doesn't simplify nicely. Have I made a mistake? This is going to be 2x squared minus 2x square root of 1 plus x squared plus 2. And common denominator here, we get a square root of 1 plus x squared minus x over square root of 1 plus x squared. Guess that's it. I was somehow expecting this to simplify to something nice. Con. Somebody want to address that? Arctan is not 1 over x squared plus 1. Yeah, so first of all, for 72, I think that says how did I expand? How did I expand this? Well, I just FOIL, right? This squared, this times 2, and that squared. Exactly, as Pratik says, this is, so arctan is not this, but rather the derivative of arctan is that. So Pratik and a few other people. Why is it not? So again, I'm not sure what what are we talking about? What are we talking about? Denominator of what now? I do have a 2x squared, right? Isaac? Okay. All right. Yeah. But look, I mean, it's important to understand what Colin was saying here, because it's a mistake a lot of people make, right? Arctan is not this. The derivative of arctan is that. And similarly, arcsine is not 1 over square root of 1 minus x squared, but rather the derivative of arcsine is that, and so on and so on. All right, let's move on. Going back to the idea of the derivative, which we saw as the instantaneous rate of change. And we saw some immediate applications in the sense that if S of t is the position, the rate of change of the position I was expecting the numerator to cancel, but I'm not seeing it. Where have we made? So I mean, without before. Oh, does it? If you distribute the denominator, well, that would have been unexpected. Let's try what Eddie was suggesting. Let's see what Eddie was suggesting. If you distribute the denominator, minus 2x times 1 plus x squared plus 2 square root 1 plus x squared. Interesting. And if you combine these two things together, factoring out a 2 square root of 1 plus x squared, you'll get x squared plus 1. Right, these two together. Minus 2x times x squared plus 1. There it is. Very nice. Very nice. So if you factor out a 2x squared plus 1, you're left with the square root minus x. And now these cancel out. That's what I was expecting. Then it didn't seem to be happening. Well done. Well done. All right. Good. Can we go over the last step? We're just canceling. It's something over itself, so it cancels to 1. So back to before that. So, hey, look, all we did was multiply that in. So multiply this by every term, you get this. And then we grouped these two, factoring out a 2 and a square root. So 2 square root, we're left with x squared. Plus, if you factor out a 2 square root, you're just left with a 1. And then this remains. And then factor out a 2 times x squared plus 1, which is present in both terms. So we factor out a 2x squared plus 1, leaving you with the square root minus the x. right? So Pratik knows where we're going with this. If S of t defines the position, the derivative being the rate of change, how fast the position is changing, at what rate is the position changing, that's the velocity. And similarly, the rate of change of the velocity, which is really the second derivative of the position, right? How fast the velocity changes? Well, that is the acceleration. Let's do a few word problems from the book, a few applications of this idea. So we're finally moving away from 224 to applications, word problems. Number 10, if the ball is thrown vertically upward with a velocity of 80 feet per second, then the height after t seconds is given by the following. So this is given. If a ball is thrown upwards at a velocity of 80 feet per second, then this is the height after t seconds. Question, what is the maximum height reached by the ball? Lilo, you'll find them in implicit differentiation. It's all the same section that we've been doing for well over a week. 80 feet per second. I mean, it doesn't really play a role here, except that this is, well, that's where it is. Right? I mean, these equations are just really working backwards. You know the acceleration due to gravity. And so the velocity is just a function whose derivative is the acceleration. So it's really working backwards. Right? We don't need to do that here. Here it was given, but in the next course, Calculus 2, that's what you'll be doing. You'll be working back. You'll be given the acceleration, and you'll ask yourself, what velocity gave rise to that? Here we don't need to worry about that. Everything is given. So, as a few people have suggested, right? I mean, first of all, the question is, what is the maximum height reached by the ball? And imagine throwing a ball upward in the air. You know what's going to happen, right? It's going to go up. The speed at which it's going up is decreasing until you reach the maximum where the speed is 0, and then it starts to fall back down. So we're really asking the question, when is the velocity 0? So the question is, what is the maximum height? And the idea is that it occurs when the velocity is 0. Right? Again, you imagine your ball going up, and then it stops and comes back down. The moment it stops, the highest point, the velocity is 0. So figure out the velocity. Velocity is the derivative of the position. So that is 80 minus 32t. And we're asking the question, when is this equal to 0? And that is easily seen to be 80 over 32. We can divide by 8, is it? 10 over 4 or 5 over 2. Exactly as the answer suggested, when t is 5 over 2. Well, let's make sure we answer the question, what is the maximum height? The maximum height will occur at 5 over 2. Well, it's all right. I mean, it's important to do that, but we still need to answer the question. So the maximum height occurs when t is 32, and this is is 3 over 2, and this is the height. So that's s of 5 over, did I say 3 over 2? S of 5 over 2, so just plug in 5 over 2 into this. That's 80 times 5 over 2, minus 16 times 5 over 2 squared. 200 minus 100, which is 100. So 100 feet, thank you, Sophia. There it is. Follow-up question? What is the velocity when the ball is 96 feet above the ground? Right, so I mean, we've established that the ball goes up to 96 to 100 feet. So of course it's going to pass 96. But what happens, right? I mean, you're throwing the ball up in the air, it goes all the way up to 100. So of course it passes 96. But what's going to happen? You're going to pass it on the way up, and you're going to pass it again on the way down. So 96 occurs twice. What is the velocity when the ball is 96 feet above the ground? So, I mean, there are really two questions, going up and going down. So let's ask the question, or let's answer the question, when does the ball reach 96 feet? Exactly, right? Find t in the position, in the height. When does the ball reach 96 feet? So let's bring everything to the other side, and we get 16t squared minus 80t plus 96 is equal to 0. Can we factor out 16 from everything? Maybe we can. 16 times what? 16 times 6 is 96. That's nice. So t squared minus 5t plus 6. And this factors as t minus 2, t minus 3, exactly as few people have suggested. And right, you've got a product equal to 0. So either t minus 2 is 0 or t minus 3 is 0. In other words, t is 2 or 3. Let's figure out the velocity, right? So at t equals 2, you're still going up, right? Maximum occurring at 2.5. And then you start coming back down. I did not mean to erase that, but we have it here again. So S of t is that. Velocity is 80 minus 32t. Velocity at 2 seconds. What is it? 80 minus 64. So that is 16. Right, so exactly at 2 seconds while you're going up, the velocity is 16 feet per second. And these sorts of textbook questions, can we assume it'll factor out with clean numbers? It usually does, but of course in real life, you need not expect these nice clean answers. So just be ready to adapt. I mean, the textbook questions are usually, unless it tells you to use a calculator, they're usually nice and clean. And exactly as Ashir suggests, if you're not able to factor, quadratic formula is always there to help you. At 3 seconds, this is going to be that minus 32, right? So 96, which is negative 16, right? So that's the deal with velocity, right? It can take on both positive and negative numbers, meaning that it offers direction, right? This is the positive direction, and then you're coming back down in a negative way. There it is. A good place to end. Questions? Anyone? So thank you all for coming. We'll pick this up again on Wednesday. We'll finish up these exercises. So, you know, in page, what is it, 235, there are lots of applications to physics and chemistry and this and that. I realize not everybody's doing these courses. If you are, have a look at them. They're nice. For our sake, we'll focus mostly on these kinds of questions. I don't care much for units. Go ahead and include them. Jake, I don't want to post anything quite just yet because some people are writing a makeup midterm. For those who are sick or had a conflict with their midterms, we're offering a makeup. Going to be completely different, but I don't want to give them an advantage of knowing the questions and the answers. So once that makeup midterm has been written, I'll post solutions. All right. You guys practice this and we'll pick this up again on Wednesday. Have a good one.